It takes a lot to keep the electricity working, not just in machinery, but in manpower. And it costs a lot of money to maintain these systems. Utilities have to maintain their lines.
In the United States, 98% of homes and businesses receive power from a vast electrical system that is woven together with a web of power lines. A grid. These power lines are naked live wires, carrying 500,000 volts. It's up to the lineman to inspect and repair every part of the grid, usually without shutting down the power.
Yeah, Bill, I was going to start making a gradual left turn and start hitting the reverse line.
One of the most daring techniques is used on very high voltage tension lines.
It's pretty dangerous, I feel, because you're mixing aviation with electricity. One, you're depending on the helicopter, everything mechanical to go right. If it goes wrong, you're going to drop out of the sky like a rock. If the lineman makes a mistake, you're going to vaporize.
These linemen and pilots work for Ag Rotors Incorporated, one of the few companies that attempts these high wire acts. Ag Rotors has the best safety record in the business.
There's linemen all over the United States that are risking their lives every day to keep the power flowing.
The dangerous marriage between helicopters and power lines is made to save money and time. Repairs that take a conventional ground crew days, Ag Rotors completes in hours.
And Bill, we're just looking for the right structure number, and then we're going to have to probably turn back a span or two once we order.
We could actually get too close to a power line and a tree, and the electricity would arc amongst all of us, and we could actually short out the power line and destroy ourselves.
If you were able to take a voltmeter, which measures voltage, and measure the voltage on that helicopter, it would be energized at 500,000 volts, and anything on that helicopter.
The metal wand gives the electricity a controlled pathway from the wire to the helicopter. Once the pathway is established, the lineman replaces the electrical connection held by the wand with metal clamps. The clamps allow the lineman to free his hands so that he can work.
I was working in the middle of the Everglades, and I knocked the bond off, unbeknown to me. And when I went to get close to the wire, the arc went straight to my mouth. So I absorbed roughly about 500,000 volts to my mouth and my nose, blew all the fillings out of my mouth, cauterized my nose, knocked me out of my seatbelt up underneath the platform, the belly of the ship on the platform, and I was unconscious, it seemed like, for a pretty long time, but it was just a few seconds.
The amount of voltage may be the first fact recited when explaining the dangers of electricity. But the high voltage isn't what kills a person, it's the amps. The electricity in the lines can flow at 500,000 volts, but isn't necessarily deadly if the amps are low. Real low. It only takes 1 amp to stop the heart.
All right, let's get back.
It takes a lot.
The wand gives the
Okay, so what's the purpose of the metal?
Measure the voltage on that helicopter, it would
All right, so this is 500,000
be
volts.
energized at 500,000.
Chopper is not 500,000 volts, right? So there's going to be a huge voltage potential difference. You don't need to be in contact if there's such a huge potential difference. The current is just going to arc through.
Volts, and anything on that helicopter.
Okay, so what you need to do is you need to move enough charges to the chopper so that the potential difference is 0.
The metal wand gives the electricity a controlled pathway from the wire to the helicopter.
All right, so there are 2 ways you could do it. Either you have to use a metal wand, or if you're not using that, what's going to happen is going to end up going through your body, right? Okay, so this is kind of like this sort of stuff that we've been discussing forever. Okay, so notice that you got the metal stick over here, and then notice that there's a wire here. Okay, you're still in contact with the metal, and then the wire is attached to the bottom of the chopper. Okay, so why is it that you're not getting electrocuted, given the fact that you're touching something metallic? All right, you're not getting electrocuted because your body becomes parallel to this current, right? Okay, so that's the reason why. Okay, once again, we had that discussion. I think we had it yesterday. Okay, so he's sitting on something which is electrified at this point.
Once the pathway is established, the lineman replaces the electrical connection held by the wand with metal clamps.
Okay, so he's using 2 metal clamps.
The clamps allow the lineman to free.
Okay, now the chopper is part of the circuit. At this point, everything is electrified, guys. Okay, these are live wires. And he's not getting electrocuted, number one, because there's no potential difference between the chopper as well as the high power
his
lines.
hands so that he can work.
Now he's free to work. And despite the fact that chopper is electrified, once again, nothing is happening to him. 2 reasons. One of the reasons is there's no potential difference, and the potential difference on top of the chopper depends on his contact points. Contact points are relatively close to each other, so there's not much potential difference. There's still current going through his body, but it's just so small that you would not even notice. And this is perfectly fine. So he makes one statement.
Working in the middle of the Everglades, and I knocked the bond off.
Okay, they have 2 bonds usually for redundancy.
Known to me. And when I went to get close to the wire, the arc went straight to my mouth. So I absorbed roughly about 500,000 volts.
Roughly about half what? 500,000
to
volts?
my mouth and my.
All right, guys, you would vaporize, so that's not true, obviously, right? So, which means that there was a small enough potential difference so that he was able to survive that. Because as soon as the if you knock up one of the bonds, the potential difference is not going to be 500,000 volts. It's going to be whatever potential difference is, probably 300 volts.
My nose, blew all the fillings out of my mouth.
So at least he had an interesting life experience that he's talking about. Anyway, into induction, maybe today or tomorrow, and then we will finish up induction this week. We're going to be only testing on Faraday's law this weekend.
See what's going on, and that's when I pulled out my camera and I noticed there was a gentleman.
All right.
Again, finder.
In shock. And then I just saw.
The only question I have is notice that he gets shocked.
Oh, but I saw on the camera. I didn't feel anything. I was just in shock.
Going across the transformer.
Looking through the viewfinder was one thing. The human.
All right. So what does a transformer do in essence? What's the purpose of it?
Change the voltage.
That's exactly what it is. Yeah, the transformer changed the voltage. It's called a transformer because it transforms current into voltage and voltage into current, right? But what's the purpose of it? I mean, what do we need a transformer for? Does it make bread taste better? I mean, what's the purpose of it?
Be more efficient.
Is it just a meaningless exercise in physics that we do to require a transformer?
Change voltage levels to transmit it more easily.
Okay, it changes the voltage levels to transfer it more easily.
You can send it over longer distances at higher voltages.
Okay, so okay, Nathan, I'm just gonna get back to what you were saying. So are you saying that it's better to transform current into voltage for transferring purposes?
Yes.
Why?
Because if you have a higher voltage, you can. Sorry, if you have higher voltage, you can have a lower current and transmit the same amount of power. And you don't lose as much, so you don't lose as much power in the lines too. So you can use a smaller wire and won't overheat and burn up.
All right, so that
too.
You can transfer power in the form of current or voltage, right? All right, so what happens if you transfer it in the form of high current?
You need fat wires and you get a lot of heating.
Resistance becomes a problem, right?
Yeah.
So larger the resistance is, the more power is going to be lost in the form of heating. And not much of it is going to be available for the consumer in the form of current at the end of the line. So it's better to transform voltage, the current into voltage, and transfer the power in the form of high voltage, right? All right, so that's what a transformer does in essence. All right, we'll get back to it. Okay, that was a firing squad. All right, so we talked about Tesla, close to 800 inventions under his name, and but he didn't get recognition for a lot of the inventions that he had. Radio, for example, he's got the original patent. Marconi won the Nobel Prize for it. X-ray machine, once again, the original patent under Tesla's name. Rankin ended up winning the Nobel Prize for this one. This is, I think, 1900 or 1901. The first Nobel Prize went to this guy. Vacuum tube amplifier, DeForest supposedly won a Nobel Prize. I couldn't find a verification on that one. But at least 2 times Tesla should have won the Nobel Prize. Yeah, by the time he died, he was penniless and almost forgotten. So what happened? Obviously, there was something that happened between Edison and Tesla. So that's something that we were discussing. All right, so let's run through the quick history and then just catch up. So Ørsted discovers in 1819 or 1820 that the current caused magnetism. And then about 10 years later, Faraday discovers that you can also generate current using magnets. And the way it is done, you need to have a current loop in a magnet and then move the magnet back and forth towards the loop. You thrust the magnet in the forward direction. Notice that the intensity of the magnetic field or the strength of the magnetic field intensifies within this area. So the current goes one way. You pull the magnet away, and the strength of the magnetic field diminishes. The current goes the other way. Current goes the other way. All right, so this becomes the Faraday's law. Simply stated, if you vary the strength of the magnetic field within the loop, it's going to cause current. This is known as the alternating current. All right, so that's one way you can generate current, and there is a second way of generating current, which involves changing the area which is exposed to the constant magnetic field. You can change the area of the loop by actually varying the area which is exposed to the magnetic field by spinning it. That's the way we normally do it today. If you spin this thing 60 times per second, the current is going to keep changing direction 60 times per second. All right, so that's the way we've been generating current for ever since 1880s. Nothing has changed. This needs to be done mechanically. You can see a hand here. You got an advanced gear system by the time you get to the coil. This thing is spinning about 60 times per second. It could be running water that could spin the coil, or it could be wind, or it could be steam. All right, so depending upon what it is that you want to use, but it's not mechanical on the left. All right, so faster you spin this thing, the more current you're going to end up getting on it. All right, so this was a really fast review. All right, so we got the lecture review material. And then go up to chapter 22 notes. All right, this time I'm going to take you guys from now on, I'm going to take you through the mathematics as well, whenever we do a review. All right, so we talked about AC versus DC. AC is the alternating current, so the direction is varying. we end up using a generator, which uses a magnet. This is the sign, alternating current sign. So this is our voltage source. Direction of the voltage keeps changing. It goes up and down. So which means that the direction of the current that is driving is going to keep changing within a certain time span. So that becomes your alternating current. Previously, we discussed DC current. That's your direct current. It's generated by a battery, and it's got a single direction. So the direction of the current is constant. Faraday's law. All right, so there's two ways of doing it. Number one, you have the loop, and you move the magnet back and forth. It goes this way and that way. So you vary the strength of the magnetic field inside the loop, so that induces current. All right, so mathematically, it's represented. You vary the strength of the magnetic field within a certain time period inside this area, so it induces current. That's what it means. That's one way of doing it. The second way of doing it is, notice that mechanically you spin the coil. So the coil is spun in that direction. So which means that the area exposed to the magnetic field is changing. All right, so you vary the area exposed to the magnetic field. So the magnetic field is constant. The area of the loop exposed to the magnetic field is varying. So that also induces current. So instead of saying we vary the strength of the magnetic field inside the loop, or just spin the loop, instead of counting the magnetic field in order to induce current, we combine both of them into the concept of flux. All right, so the flux is the amount of magnetism intercepted by an area. Right? So this is the area of the loop that intercepts the magnetic field. All right, notice that this is a dot product. So you got your dot here. All right, so you got two vectors, dot product. So you're interested in the component of the magnetic field along the direction of the area vector. All right. So the component of the magnetic field along the direction of the area vector can be given by the cosine of the angle that we're looking at. Anyway, so flux is a combination of the magnetic field intercepted by the magnitude of the area, or the size of the area is a vector. So any change in flux is going to induce current. This becomes the Faraday's law. Change in flux involves either the changing the strength of the magnetic field inside the loop, or area of the loop exposed to the magnetic field is going to keep changing. All right, so it's got two interpretations. All right, so any variation of the flux induces current. So the next question is, change in flux, does it induce current or does it induce voltage? So now we have to get into physics. So the current, we know that what drives current is the voltage. All right, so voltage is what drives current. Voltage means we'll have two different regions, and they will be separated, and there's going to be an electric field. An electric field acting on the charges will cause a force, and charges will accelerate, and blah, blah, blah. Okay, so that's what it means. So change in flux is going to generate an electric field inside the wire that, in essence, is going to drive the current. All right, so change in flux induces voltage, and voltage is what drives current. All right, so there's an adjustment to the formula that we will discuss. And the variation of flux is going to induce voltage, and there's going to be a negative sign. It's going to give us the direction of the current by the Lenz's law. So the Lenz's law is something that we will discuss today. All right, so let's skip ahead. All right, Faraday. Everything that we've been discussing so far came out of the genius of Faraday, who could not do mathematics. Okay, so you change the flux through a single loop, and you will get a certain amount of voltage, and you will get a certain amount of current. If you double the loop, the voltage is going to double. If you triple the loop, the voltage is going to triple. If you make this 4 times larger, the voltage is going to be 4 times larger. If you make it 5 times larger, the voltage is going to be 5 times larger. All right, so which means that you can increase the strength amount of voltage that you generate by increasing the number of loops, or you can diminish the amount of voltage you get by changing the number of loops. All right, so the number of loops go up, the voltage goes up, the current goes up. Number of turns go down, the voltage goes down, the current goes down. All right, so we are changing the notation at this point. Instead of using voltage, we're going to go back to a more classical notation. This is known as EMF. EMF means electromotive force. This is the force that drives the charges. All right, so the voltage is a modern concept. When I say modern, this is like early 20th century, late 19th century, more like it. EMF, physicists didn't know what was driving the charges, so they decided to call it electromotive force. All right, so traditionally, this is what we end up using. All right, so summary statement of the Faraday's law. Change in flux is what generates the electromotive force. And you can change the strength of the electromotive force by increasing or reducing the number of turns. And electromotive force is what drives current. Obviously, resistance is what diminishes it. Okay, so that's the Ohm's law. Okay, so that's a summary statement of everything that we came up with.